SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we were discussing about the diffusivity of turbulence, one very important attribute for turbulence. The diffusivity relates to the enhanced diffusion that you see in a turbulent flow and enhanced compared to laminar flow. And we discussed a case study of heat transport in a room in order to demonstrate how fast diffusion is in a turbulent flow. So we started by looking at, say, a room that has maybe a heating element like a radiator installed, a characteristic length L, which can be approximated as the cube root of the volume of the room for all practical purposes. And we took the first case where there is no air motion, and if there is no air motion, the heat distribution, the heat transport can be governed by this heat transport equation shown here, equation number 1. Del theta del T is gamma del squared theta del xi del xi. Now again, our goal is not to solve this problem, to come up with an answer for the problem. Our goal is to try to understand the consequences of a turbulent flow. So in the context of this particular problem. So what we did was we dimensionally analyzed this problem. We did an order of magnitude analysis. On the left hand side it became delta theta over Tm, Tm being some kind of a time scale associated with this problem, so a characteristic time scale. The m subscript was used because it is only molecular diffusion here, correct? Instead of heat transport due to turbulent flow. It is only molecular diffusion, there's no airflow. So we are using the subscript m and we represent the characteristic time scale as Tm. On the right hand side of equation 2, we have gamma delta theta over L squared. Gamma being the thermal diffusivity, and then you have delta theta over L squared. L is again the characteristic length scale. So instead of the del xi twice, we are writing it as L squared. So from here you can solve for Tm being approximately L squared over gamma. Now L, say it is of the order of 5 meters. A typical room, reasonably sized room, L characteristic length scale is 5 meters. Gamma, values for air at standard temperature and pressure, if you use those, you get your Tm to be of the order of 100 hours. So that is the amount of time that it takes for heat to be transported in a room of that size. Very high, isn't it? Now consider turbulent flow. Even if you have weak motions due to some kind of a density stratification within that room, even a room as high as 5 meters, you will have some kind of airflow due to small density changes. So here the time scale, if you want to estimate it, it will be dependent on the velocity because there is flow. You cannot estimate it from the properties of the fluid inside, which is air. You need the velocity scale. So L over U. Turbulent time scale is L over U. U being an RMS amplitude. And then that led us to try to estimate the RMS amplitude. So we said, okay, let's say there is a buoyant acceleration of the order of g delta theta over theta, and that approximately comes to 0.3. So if you estimate the kinetic energy per unit mass, it comes to 0.03 meters squared per second squared. Velocity comes to 17 centimeter per second, calculated from the kinetic energy. So characteristic velocity scale of 5 centimeter per second is reasonable. So using this U, RMS amplitude of approximately 5 centimeter per second and an L of 5 meters, we came up with a turbulent time scale of approximately 2 minutes. So that's the difference, 100 hours in a laminar flow versus 2 minutes in a turbulent flow. That alone showed you how fast the mixing was in a turbulent flow. And one additional point that we made in the last class was that you can have eddies that are as small as 1 centimeter. Okay, the 1 centimeter number comes from other dissipation equations, not shown here, will be described much later in this class. But 1 centimeter eddies as small as 1 centimeter, they dissipate due to molecular diffusion. Their viscosity does play a role. And the time scale for that is L squared over gamma. Obviously, L, small l being 1 centimeter and gamma being the standard value for air at standard temperature and pressure. So that would be a few seconds. So at the small scales, it dissipates in a few seconds. And this point is important when we want to discuss a few topics today in today's class. So that takes us to the conclusion that diffusion by random motion, again, it is not particularly random, but Tennekes and Lumley calls this random, isn't it? It is seemingly random according to the modern definition of turbulence. This is very rapid compared to what would happen only due to molecular diffusion. And that's what we saw. 100 hours versus 2 minutes. So now let's think about these time scales a little bit more. The ratio of the turbulent time scale, Tt, to the molecular time scale, which is Tm, okay, becomes the inverse of the Peclet number. How is that? So I have Tt over Tm. Tt is L over U, isn't it? And Tm is gamma over L squared. Okay, Tm is obviously a molecular property, molecular time scale. Tt is a flow property. That's the difference. If you take the ratio of the two, Tt over Tm, one of the L's gets cancelled out and you get something like gamma over UL. This is 1 over Peclet number, because Peclet number is UL over gamma. Just like Reynolds number is UL over nu, where nu is the kinematic viscosity or momentum diffusivity. Peclet number is UL over gamma, where gamma is the thermal diffusivity. Nu is kinematic viscosity, or another way to call it, since we are calling gamma as momentum diffusivity, gamma as thermal diffusivity, this one would be momentum diffusivity. Just as long as we are naming them in terms of diffusivity, I just want to stay consistent here and call nu momentum diffusivity. So this ratio of the turbulent timescale to the molecular timescale becomes the inverse of the Peclet number. Now, let's go a step further. And since we are talking about flow in a room, it's air, it's obviously a gas. Typically for gases, gamma is of the same order of magnitude as the kinematic viscosity. In fact, nu over gamma, okay, ratio of momentum diffusivity over thermal diffusivity is the Prandtl number. And for air, it is 0.73. So order of magnitude of 1. So meaning nu is of the same order of magnitude as gamma. Momentum diffusivity is of the same order of magnitude as gamma for gases. So in that case, your Tt over Tm can also be written as nu over UL. Like this, which is 1 over Reynolds number. So essentially, the inverse of Peclet number just became the inverse of Reynolds number. So that gives you an idea now. The ratio of the turbulent time scale to the molecular time scale is 1 over Reynolds number. So think about it. Increase in Reynolds number, your turbulence increases. Turbulence gets to be more vigorous. The turbulence intensity increases. And when that happens, the 1 over Reynolds number becomes an even smaller number. So the difference between the turbulent timescale and the molecular timescale becomes even larger. As the Reynolds number increases, the difference between the turbulent timescale and the molecular timescale becomes even larger. So that's one way to look at the ratio of the turbulent timescale to the molecular timescale. Now, for this example here, okay, the Reynolds number is approximately 15,000 based on the velocity, the the viscosity of the air, the length scale and all that, Reynolds number is approximately 15,000. So you can think of this Reynolds number again as a ratio of the turbulent time scale to the molecular time scale that would prevail in the absence of turbulence in a problem with the same length scale, isn't it? And I'm going to explain this point a bit more. The Reynolds number may be interpreted as the ratio of the turbulent time scale to the molecular time scale. Which molecular time scale? The molecular time scale that would prevail in the absence of turbulence. Because if I look at this Tm, this molecular time scale came from the case study, right? The case study when we considered no airflow, only molecular diffusion. That is what I mean by that would prevail in the absence of turbulence in a problem with the same length scale. And this is Tennekes and Lumley's interpretation of the Reynolds number. It's a very interesting observation. So according to them, this point of view is more reliable than thinking Reynolds number is a ratio of inertia over viscous. So always when we bring in Reynolds number, we say, okay, it is rho ul over mu or ul over nu as in kinematic viscosity, and then we say it is the ratio of inertia over viscous forces. Nothing wrong with that. According to Tennekes and Lumley, you want to consider Reynolds number more as a ratio of the turbulent time scale to the molecular time scale, as in the ratio of time scales rather than the ratio of the forces, the inertia to the viscous terms. Why is that? So according to them, this ratio of inertia to the viscous terms in the Navier-Stokes equations, right? So again, I want to sort of repeat this here, but you have u dot del u is minus 1 over rho del p plus nu del squared u. Now if I do an order of magnitude analysis of inertia over viscous, I will get exactly ul over nu. I will get ul over nu, which is the Reynolds number, correct? And this is inertia, this is viscous. But according to Tennekes and Lumley, it is more reliable to look at Reynolds number as the ratio of time scales. Why is that? Because the viscous effects start to dominate more at the smaller length scales. Isn't that true? So when we are talking about a turbulent flow, we have a wide range of length scales. The viscous effects become more important at the smallest length scales when, in order to dissipate the kinetic energy at the small scales. Viscosity plays a role in dissipation, and dissipation happens at the small scales. So one can argue that viscous terms are more dominant only at the small scales. At the larger scales, at the intermediate scales, inertia terms are more dominant. So when we consider Reynolds number to be the ratio of inertia over viscous, both are dominant at different ranges of length scales. So the Reynolds number being inertia over viscous, these are at large scales, or I would say intermediate scales as well, and these are definitely at small scales. So then we are comparing two quantities that are dominant at different ranges of length scales. So is it fair to consider Reynolds number as a ratio of those two terms, is what Tennekes and Lumley are arguing. What they are saying is that why don't we just consider it as a ratio of time scales, the turbulent time scale to the molecular time scale. That's their argument. So that takes us to this concept called eddy diffusivity. Now, when we considered airflow when we consider the room case without airflow, so only molecular diffusion, we could represent the entire heat transport through one single equation, say the heat transport equation. And that was del theta del T is gamma del squared theta del xi del xi. So one would be very tempted to treat, say, the diffusive nature of turbulence also through such an equation. It would be nice. So instead of using a thermal diffusivity, which is obviously a property of the fluid and that cannot be applied here, what if we could represent it by an effective diffusivity? Meaning, what if we could represent it by this equation here? So del theta del T looks exactly like the heat transport equation I had shown earlier, where only molecular diffusion exists. So instead of gamma, the thermal diffusivity, we are now representing it by K, some kind of effective diffusivity. The biggest problem with doing this is now we are treating turbulence as a property of the fluid rather than the property of the flow. And this conceptually is wrong, right? But mathematically, it is easier to understand. There is transport, we have mixing, except it is mixing at a much faster time scale. So what if it is the same mechanism, but now it is at a much faster time scale? Meaning, say you have diffusion happening at a very, very high gamma value. Is that possible? So mathematically it is easier to understand. Conceptually it's a very dangerous thing to do, because that is not the case. One of the attributes is that turbulent flows are flows and not properties of fluid. So this violates that right there. However, just so that we can understand the process, we'll go with this. Del theta del T is K del squared theta del xi del xi. So K is this effective diffusivity. As you know, K is going to be my eddy diffusivity, but we'll see how that is. So now, if this has to represent reality, what is reality? I have turbulent flow in a room, right? For it to even have a crude representation of the reality, I've already made a huge assumption. But let's say I want to use this equation to represent the turbulent flow in a room. Then you have to choose K such that it is realistic. Okay? So you have to choose the value of K such that the time scale of this hypothetical turbulent diffusion process. Why do I call it hypothetical turbulent diffusion? Because it is actually not diffusion in the true sense of the word. Molecular diffusion is diffusion. Mathematically, it's a second derivative term. That is not what is happening here, but we are representing it like that. So that is why we are calling it hypothetical turbulent diffusion process. So we have to choose K such that the time scale of this turbulent diffusion, hypothetical turbulent diffusion process, is equal to that of the actual mixing process, right? As in turbulent mixing process. So let's say the time scale associated with the above diffusion equation, T is approximately equal to L squared over K. And this is how I could do it when I want to estimate the time scale, right? So this would be delta theta over T is approximately equal to, order of magnitude analysis is K times delta theta over L squared. So from here delta theta and delta theta get cancelled and T is approximately equal to L squared over K, which is essentially what I wrote here in equation number 7. So now this is the time scale associated with my newly manufactured equation representing the turbulent transport of heat in the room. Now obviously this has to be equal to the turbulent time scale. Only then can you choose the value of K. So if you equate this to Tt, the turbulent time scale, you obviously get K to be equal to UL, because Tt is approximately equal to L over U. So L squared over K is equal to L over U, so K is approximately equal to UL. So that is your effective diffusivity. The RMS amplitude, like we had discussed earlier, multiplied by the characteristic length scale. So now let's compare this to the kinematic viscosity, the momentum diffusivity or the thermal diffusivity. So let's say I take K over gamma, which for gases is the same as K over nu, isn't it? Because these two, gamma is of the same order as nu, isn't it? For gases. And we are considering gases here, air. So K over nu, so since K is UL, so it becomes UL over nu. So K over gamma or K over nu becomes equal to Reynolds number. Think about this. Ratio of the effective diffusivity to the momentum diffusivity is the Reynolds number. So higher the Reynolds number, higher is your effective diffusivity compared to the momentum diffusivity. Obviously, we knew that earlier, right? Turbulent produces enhanced diffusion. So higher the Reynolds number, higher the turbulent flow, larger the intensity, and more effective the mixing is. So higher the effective viscosity is. That is your eddy diffusivity. Eddy diffusivity has to do with the effective diffusivity in a turbulent flow. K is your eddy diffusivity, and the ratio of the eddy diffusivity to the momentum diffusivity represents the Reynolds number. Order of magnitude. So in the next problem, we are going to look at the diffusion with an imposed time scale. Here, in the previous problem, we looked at diffusion with an imposed length scale, whereas now we are going to look at it with the imposed time scale. And the problem we are going to look at is boundary layers in the atmosphere. So I want to make sure you understand this. We looked at flow in a room, right? Turbulent flow in a room. And we tried to find out the turbulent time scale associated with that flow in a room. And we realized that it is actually much smaller than what would exist if you only had molecular diffusion. 2 minutes versus 100 hours. Then what we tried to do was that we tried to see, okay, what is the ratio of the turbulent time scale to the molecular time scale? And that turned out to be the inverse of the Peclet number. It also turned out to be the inverse of the Reynolds number due to the fact that the momentum diffusivity is of the same order of magnitude as the thermal diffusivity for gases. So that tells me that as the Reynolds number keeps increasing, my turbulent timescale is keeping on decreasing compared to the molecular timescale. So the difference between the turbulent timescale and the molecular timescale is widening, is increasing. And this brought about a very interesting observation, especially as presented in Jennings and Lumley's book, where they argued that it is better to consider Reynolds number as a ratio of the turbulent timescale to the molecular timescale, rather than the ratio of inertia to the viscous terms. And this has to do with the fact that this has to do with the role that viscosity plays in dissipation. As you know, dissipation happens at the small scales. You have the large scales breaking up into the small scales. You have energy being transferred from the large scales to the small scales. Eventually, it is going to break up into even smaller and smaller scales until viscosity just completely takes over. Once viscosity takes over, the energy just dissipates. So, viscous effects are more dominant at the small scales. So then when you consider Reynolds number as the ratio of inertia over viscous, aren't they acting at two different scales? Then is it fair to take the ratio of those? So that was their argument. So instead of that, why don't we consider Reynolds number as the ratio of, technically 1 over Reynolds number as the ratio of turbulent timescale to the molecular timescale. This took us to the concept of eddy diffusivity. And in eddy diffusivity, the argument was where we are violating one rule by considering eddy diffusivity, because we are trying to represent the turbulent flow like we would represent molecular diffusion. So like a heat transport equation. Del theta del t is k del squared theta del xi, where k becomes the eddy diffusivity. So this is like the heat transport equation, right? Instead of gamma in molecular diffusion, instead of thermal diffusivity, we have k alone. So now you have this eddy diffusivity or effective diffusivity, which is supposedly going to represent our turbulent diffusion. Again, keep in mind, this turbulent flow is used as enhanced diffusion. Diffusion is actually molecular diffusion. Okay, technically diffusion is only molecular diffusion. We are calling it enhanced diffusion because it has the same outcome. Remember in module 1 we had discussed that it has the same outcome. So we look at the time scale associated with this equation, and it is L squared over K. Now for it to represent reality, it has to be the same as the turbulent time scale, isn't it? So it has to be L over U, the turbulent time scale, in which case we come up with an estimate for the eddy diffusivity, which is UL. And even if you take the ratio of the eddy diffusivity to the thermal diffusivity or the momentum diffusivity, since for gases thermal and momentum diffusivity are of the same order of magnitude, you get the Reynolds number again. So eddy diffusivity to momentum diffusivity becomes the Reynolds number. So as Reynolds number increases, the eddy diffusivity increases compared to the momentum diffusivity. So this was the analysis for turbulent flow in a room where you had a problem with an imposed length scale. And in the next class, what we are going to do is we are going to look at a problem with an imposed time scale. And specifically, we are going to look at the boundary layer in the atmosphere and try to estimate time scales and eddy diffusivities based on that problem and see how it looks like. Thank you.